We're going to now look at the sums and intersection of two vector spaces. And if you may remember, like let's not take a look at vector spaces right now. If you just remember, if you have two sets, A and B, let's denote them as regions in the plane here. Then we know that A union B, this was the collection of elements, C such that, well, let's write it down here. This was the collection of elements C such that C is an element of A or C is an element of B, right? You think of this or as, and what that is kind of geometrically here is anything, or it's the collection of all elements that are in A and in B, right? What about the intersection, right? This was the union. What is the intersection? A intersect B. This is point C such that C is in A and C is in B. What are those, right? Those points are, it's the overlap. You think about the intersection as being the overlap, right? So you, in fact, you have the intersection as a subset of the union here. You recall these notions, but when we're looking at vector spaces, we don't really say union, we say sum. So let's give a definition here. The sum V plus W, let's use U, I think, of vector spaces U and W is defined to be the following thing. So we'll write V, how about U plus W is defined to be, and again, this is going to be elements, let's say U, such that U is an element of U or U is an element of W, right? So the sum is basically, you think of it as the union, but we call it the sum because we have an addition operation defined on vector spaces now, right? And so now we're thinking of the sum as being the sum of two vector spaces, not necessarily just the union of two sets with no underlying structure on them. The intersection, and this is the same notion here, so we'll write U intersect W is defined to be the following thing here. So we have U intersect W is equal to the set of points Z such that Z is an element of U and Z is an element of W. So geometrically, or if you have a picture in the back of your head, you can really keep this picture of union for sum and intersection for intersection, right? It's just now there's some structure, there's underlying structure going on, right? In this general construction for union and intersection, there's no structure being assumed of addition, scalar multiplication, things like this, right? We're purely describing collections or families of elements within a given set, right? Now we're doing the same thing in the context of vector spaces, but there is some structure going on, right? Now we have this notion of scalar multiplying. Like you take an element of your set and all of a sudden you can scale it or you can add it to another element, right? And so there's some additional structure here that's going on. There's a very, very important type, if you will, of vector sum, and that's the direct sum. So let's let V be a vector space with U and W. So let's say U and W are both contained in V. These are vector subspaces. Remember, if you're a subspace of a vector space, that means you're a vector space yourself, right? So U and W here, they are vector spaces with the operations from V, just kind of restricted to those subsets, right? Let's say that these are two subspaces, and let's assume, or let's not assume, I don't like that language. Let's say U and V are two subspaces such that U intersect W is just the origin. Then the sum of U and W is called the direct sum. And we write it denoted as U direct sum W. So you circle the plus here, right? This is the direct sum. The direct sum is a very important concept, and we'll explore briefly why it is so important in a little bit. But first, I have a claim. I have two claims. So the first claim is that U plus W is a vector space. And the direct sum, U plus W. Proof. This is an exercise. I want you guys to prove this. This is a very good thing if you can, right? So you assume that U is a vector space and that W is a vector space. And I want you to prove that U plus W is also a vector space. So the sum of two vector spaces is a vector space. I have another claim that for U and W vector spaces, we have that U intersect W is a vector space. Now this one we'll prove together. Okay. Showing that the sum is a vector space will have a similar flavor, but there will be noticeable differences because of the noticeable differences between vector sum and intersection of vector spaces, right? So what do we need to show? Remember, what was the subspace criteria that we were talking about in the previous videos? Well, we were saying that, you know, for to be a vector space, that's the same as being a subspace, right? So let's start with that. To show U intersect W is a vector space, it suffices to show that U intersect W is a subspace of V. Because remember, these are vector spaces contained in V, and we learned and have proven actually that there's a one-to-one correspondence between subspaces and vector spaces, right? So instead of having to go through all of these axioms for the intersection, it suffices to go through this subspace criteria here, right? Or this procedure we had, this test for determining if three things were a subspace. And you don't have to remember all of the details. You have to be able to flush out all of the details. But what you do have to be able to remember is what three questions to ask yourself, right? When you're asking yourself if something is a subspace, you have to ask, is 0 in my space? So we have to ask, is 0 an element of U intersect W? We have to ask, is U intersect W closed under addition? We have to ask ourselves, is U intersect W closed under scalar multiplication, right? If we can answer yes to all three of these things, then we've effectively proven that U intersect W is a subspace, therefore proving that it's a vector space. So let's recall what U intersect W is, right? This is the set of points Z such that Z is an element of U and Z is an element of W. Well, if Z, right, let's just start with what U is. U is a vector space, which implies that 0 is an element of U, and W is a vector space, which implies that 0 is an element of W. Well, by the definition of the intersection, this implies that 0 is an element of U intersect W, right? First one is verified. We've shown that, right? Because to show that it belongs to the intersection, it suffices to show that it belongs to both sets constituting the intersection, right? The two sets that you're taking the intersection of, to show that it's in the intersection, you just have to show that it belongs to both of them simultaneously, which is what we've done here for the identity element. And this relied on the fact that U and W were themselves vector spaces, right? We need to show that it's closed under vector addition. So we need to start with V1 and V2, an element of U intersect W. Well, if this is true, then V1 and V2 are an element of W. This implies that V1 is an element of U and V2 is an element of U. Well, we know that U is a vector space, so U is closed under vector addition, which implies that V1 plus V2 is an element of U. But we have the same argument for W, right? So U, this was for U being a vector space, and now since W is a vector space, this implies that V1 in W and V2 in W implies that V1 plus V2 is also in W, right? And since this is also in W, well, now we've seen that the sum V1 plus V2 is in U and it's in W, which implies that V1 plus V2 is an element of the intersection, right? So we've shown that the intersection of two vector spaces is closed under vector addition. Lastly, what about scalar multiplication? So let's let V1 be an element of U intersect W. This implies that V1 is an element of U, and this also implies that V1 is an element of W. But U is a vector space, which implies for all A and R, A V1 is an element of U, and W is a vector space, which implies that for all A in R, A V1 is an element of W. Well, this implies that A V1 is an element of U intersect W, because we've shown that A V1 lives in both U and W. Thus, we've shown that the intersection is closed under scalar multiplication, but in total, we've shown that U intersect W is a subspace of V, which means by the previous theorem, we've shown that it's a vector space itself. Okay, and I want to wrap up the discussion of sums and intersections with the following theorem. We have that the dimension here, so, let's let U and W, these will be two vector spaces. We have that the dimension of U plus W is equal to the dimension of U plus the dimension of W minus the dimension of their intersection. And you may ask, well, where does this term come from, right? Well, if you think about, you have U, V, or U and W, and then you have their intersection here. Well, if you count all the basis elements of U, right? You know, maybe there's like U1 through UK here. You count all the basis elements of W, and there's like W1 through WL or something like this. Well, for everything in the middle that belongs to U and W, you've counted that twice, right? Because you counted it once for when it belongs to U, and you counted it once for when it belonged to W. And since you counted that twice, you need to subtract off one copy of all those things you counted. And that's exactly the number of elements that you counted twice, right? Which is the dimension of the intersection. So that means when U intersect W is just the origin, we have that the dimension of the direct sum is equal to just the dimension of U plus the dimension of W. And this is why we care so heavily about direct sum spaces, right? Like, for example, you would say R2 is equal to the direct sum of R and R, right? You get this dimension counting that behaves in a way that you would want it to, right? If you take the dimension of a three-dimensional, or if you take the sum of a three-dimensional space and a five-dimensional space, and then you get a six-dimensional space, like that's a lot less, like that behaves a lot less nicely than what you would want to work with, right? You would want to work with something that's, okay, I have a six-dimensional space, or excuse me, I have a five-dimensional space and a three-dimensional space. When I sum these spaces, I better have an 8-dimensional space that I'm working with here, right? That's the idea of a direct sum, which is why it's so important. Okay, so really, I think this is all I want to discuss for now. Over vector spaces. Next, we're going to start looking at linear transformations of vector spaces, and then we're again going to study the concepts of being one-to-one and onto, which are injective and surjective respectively, right? And when both of those are satisfied, we have a bijection, which is called an isomorphism, et cetera, right? So we want to understand all of those notions as well in the context of an abstract or an arbitrary vector space.